The neural processes underlying learning and memory are very complex, but one of their main features is synaptic plasticity, the strengthening and weakening of synaptic connections in an experience-dependent manner. The detailed mechanisms causing synaptic plasticity are still a matter of great debate, but at a functional level, many examples appear to fall into a category known as Hebbian modification. Hebbian synapses are synapses whose strength is increased when the pre- and post-synaptic neurons are active together. In its simplest form, this means that when an excitatory Hebbian synaptic input is temporarily paired with a spike in the postsynaptic neuron, the synapses get strengthened. This means that the synapse is likely to be more effective the next time it's activated. Conversely, if the postsynaptic neuron doesn't spike following the Hebbian input, the connection doesn't get strengthened, or it can even get weakened. The bottom line is, neurons which fire together wire together, while neurons that fire out of sync lose their link. There's no direct evidence that any real synapse displays the Hebbian properties of the simple sort I just described. However, Hebbian-type mechanisms may well underlie some of the important forms of learning which occur in the nervous system, such as long-term potentiation, or LTP, and classical conditioning. LTP is the long-lasting enhancement of a particular synaptic pathway that results from a brief, high-frequency activation. This tutorial will show you how LTP can be implemented in AnimatLab using Hebbian synapses. First, we need to create a new project. A copy of this tutorial is available in the AnimatLab Tutorials Neural Networks folder. Please choose where you want to create this project and then call it LTP. Now let's create a new organism and open its behavioral editor. We need to add two spiking neurons to our diagram. Now we need to add a synaptic connection between those neurons. We'll be using a Hebbian acetylcholinergic synapse. This is one of the predefined spiking chemical synaptic types. The most important differences between this synapse type and the standard nicotinic acetylcholinergic synapse are found in the Hebbian properties section. This synapse has the Hebbian flag set to true, so it will use Hebbian learning. Hebbian learning is accomplished by keeping a small, short-term memory of when Hebbian input spikes have occurred. This is the Hebbian time window parameter. The synapse has a base conductance value. When the postsynaptic neuron spikes, it checks its memory to see if the presynaptic neuron has also spiked within the time window. If it has, then it uses the formula on the screen to calculate how much the conductance needs to be increased. The amount of increase is determined by how long ago the presynaptic spike occurred and on the learning increment percentage value. However, the conductance is constrained to never grow above the value defined by the max augmented conductance value. In addition, it's also possible to have these learned changes slowly fade out and be forgotten over time if they're not reinforced. This can be done using the allow forgetting flag. This property is controlled by the forgetting time window and the consolidation factor. If the consolidation factor is 1, then the synapse type forgets at the same rate irrespective of the degree of training. In this case, the augmented conductance simply declines back to baseline linearly during the forgetting time window. If the consolidation factor is greater than 1, though, then more strongly augmented synapses forget more slowly. For these synapses, the forgetting time window is extended by some fractional degree of augmentation and the amount by which the consolidation factor exceeds 1. For more details about how Hebbian learning is implemented in AnimatLab, please review the documentation. Next, we need to make a couple of changes to the neurons. First, select neuron 1 and set its relative accommodation to 0. This means that its threshold will not adapt due to firing bursts of action potentials. Now select neuron 2 and set its after hyperpolarization conductance to 1.5 microsiemens. This sets the conductance increase that occurs immediately following a spike. Now let's create a line chart so we can watch the membrane voltage of our two neurons. We're only interested in a small time window in this tutorial, so let's specify the start and end times for this chart and set the end time to be 0.3 seconds. Also, an important point when using charts is that we need to set the sampling rate of the chart to match the time step of the neural simulation. If we leave it at the default of 5 milliseconds, then we'll be sampling so slowly that we'll not catch any of the spikes in our chart. You can find the time step of the realistic neural module by going back to the behavioral editor and looking at the tab for neural modules. Now we need to add a stimulus to neuron 1 to cause it to fire a burst. However, we don't want it to fire a high-frequency burst just yet. We'll give it enough current to produce a low-frequency spiking. Set the start time to 10 milliseconds, end time to 260 milliseconds, and the current to 21 nanoamps. Now let's run the simulation and look at what happens. Neuron 1 produced some low-frequency spikes that caused excitatory postsynaptic potentials in neuron 2, but no spiking. Now let's add another stimulus to neuron 1 that will cause it to produce a brief high-frequency burst in the middle of the other burst. Set the start time to be 110 milliseconds, end time to be 160 milliseconds, and let's leave the current at 10 nanoamps. Run the simulation again, and this time we can see that the high-frequency stimulation did cause neuron 2 to spike, and that after the high-frequency burst, the conductance between neuron 1 and 2 has now increased to the point where even the low-frequency burst can generate spikes in neuron 2. What's the mechanism for LTP? One could imagine a presynaptic mechanism such as an increase in transmitter release, or a postsynaptic mechanism such as an increase in receptor sensitivity. LTP almost certainly has a presynaptic component, since it is specific to the pathway stimulated. However, most forms of LTP also have a postsynaptic component. This can be demonstrated as follows. Let's disable the second stimulus and then add an identical one to neuron 2. Now, the presynaptic neuron doesn't change its activity throughout the sweep, but instead, current is injected into the postsynaptic neuron to increase its activity. After the postsynaptic spikes, the EPSPs from neuron 1 are enhanced, although not in this case to the level where they elicit spikes. If we increase the amplitude of the stimulus in steps of 20 nanoamps to elicit more vigorous spiking in neuron 2, then we can see how the amplitude of the EPSPs is further augmented. Once we reach 50 nanoamps, there's super threshold and elicit spikes in neuron 2. This shows that the increased level of postsynaptic response is an essential feature to trigger LTP. Current thinking is that the key event is an increased inflow of calcium into the postsynaptic neuron. Furthermore, since we've already seen that there is a presynaptic component to LTP, this result implies the once heretical notion of a retrograde transmitter. This means that the postsynaptic neuron releases some substance when its activity level increases. The substance has an effect back across the synapse, most likely onto the active presynaptic terminal. Current thinking suggests that nitric oxide might be a retrograde transmitter in the central nervous system. This tutorial has shown you the basics of how to implement LTP using Hebbian synapses in AnimatLab.